Hi ladies and guys, it's Wiley and I'd like to discuss with you today the Redstone pen mod, in particular the Redstone logic controller, the RLC. So I could see on Curse and different other forums that there were nice discussions about it and code was shifted around and so on, but I could also recognize that there were continuous requests for kind of beginner guides in video form. So I'll try to do that and I'll try to keep it beginner friendly so that we don't rush through the features and instead changing some signals, look how the values change when we do signal changes and so on. So we try to keep the pace in a way that beginners can follow. Right. I recommend that we start off with building an RLC and after that get it out of this Botania area where there are too much eating and burning noises and find a nice and quiet place where we can put it down and then start coding. Okay, so for building one we will need a redstone for a redstone quill in the beginning and then a feather, it's also for the redstone quill. And now the Redstone logic controller has some ports on the sides and the port colors are reflected with items that we put there. So there's a blue, a green, I have already green, so blue and then a red port. Okay, so that's what we need. Now let's place this all down in a crafting grid. So that's the quill and we put that in the center, then at the corners we got the quartz and then the items representing the port colors. And here it is. I have already two levers and let me double check something. It is already some time ago when I played last time, so I had already some controllers as well. But anyway, we wanted to build one, so that should do. Maybe something with inventory so that we can double check the comparator override reading. Yeah, that'll do. Okay, now let's find a nice and quiet place. This one is nice but not quiet and also not decorated yet. This one will be too loud in a minute because that's about to be full. And then the ore processing will start, the Botania ore conversion, and that's also a loud process. Yeah, so this is a small world where my wife and me are occasionally playing once we get time. And up there is the Botania area where I do the automation. We also have a small village with a lot of her. We don't go up there, we go into the basement where we started off. Yeah. Okay, anytime I run out of coffee, I will cut. But let's first see how the controller is placed. So you can already see when I hover the block where I want to place it on, that I can decide in which direction I place it. So if you change your setup, then you can also change the direction of the RLC accordingly, and you can also place it on ceilings and on the walls. So let me place this one down, for example, here. Then we get a redstone lamp. Do I need the second one? Nah, probably not. Okay, redstone wire here, and then I'd like to have two redstone lines with different lengths so that we can have different signal strengths. So we got 15 here and we got 13 here. I think this will do for the basics. Okay, now let me grab a coffee and then let's get started. Okay. Okay, it's just a few coffees later. It's already next weekend. If I recall correctly, we managed to craft an RLC, find a nice and quiet place, place it down, and put some kind of mundane circuitry around it. And now the next obvious thing would be to start coding. So we open the UI and take a look how this looks like. So we got the port list over here. The signals are shown as these numbers, then the characters, the letters, are the values that we use in our program, and the port colors, well, not much to say about that. We got a pictogram, how the block looks from the outside, so that you don't need to close the UI, look up and so on. We got a run stop button. As a context, if the program is stopped, which is the default when you place it, then you can edit the program, but the block won't do anything. If you press play, then you are in run mode, then you can't edit anymore, but the block is functioning. Next to that, there is paste and copy. So if you have contents in your editor, like the comment I enter now. Then we got a copy mode, and hoppala. And if the editor is completely empty, then we are in paste mode. So quite simple, and it allows you to quickly transfer programs from one RLC to another one. So next up would be the documentation. It's a tooltip documentation, a quick reference over here at the left side. And that is deliberately not done with a book, because with a book you would have to close the UI to look something up, look it up, or reopen the UI, and then think, what was I actually doing? So the quick reference might be much more helpful than a book in this case. And then there's a free area over here, which is only interesting for very few players, because you can connect the RLC, your client PC actually, to the outside world, for example an Arduino or Raspberry Pi, whatever you like to program, and transfer those signals into Minecraft and vice versa. And this looks then like a small chip somehow. If you hover it, then you will see to which PC this RLC is connected to. As said, it's not interesting for most players, and it doesn't have any effect according to performance, server performance, and so on. It's only interesting for the people who like to do a bit more with electronics. Okay, so now to start up with coding, we need to know what logic processing means in the context of this RLC, because logic signals are on-off signals, and Redstone signals are, well, signals between 0 and 15. But if we take a look how vanilla blocks work, they are actually logic blocks if we exclude the comparator. So a redstone lamp is something like a redstone consumer, and it is lit if it is somehow powered. So the redstone lamp has an input, a logic input, and if the logic signal, or if the redstone signal coming in is at least 1, then the lamp will be lit. And if it is 0, the lamp is off. If we take a look at redstone producers or redstone sources like a lever, buttons, whatever, they always output 0 or 15. So on means 15, off means 0. I'm not telling you anything new now, but this is how the RLC interprets logic values, because it's the only sensible way in Minecraft to do that. We could make special data types for Boolean values, so special for on-off values and so on, but we don't need that. We can directly work with numbers if we know that inputs work like redstone lamps. So if it is somehow greater than 0, then it is interpreted as on, and outputs are either 15 or 0 for logic signals. Okay, let's type some code and experiment. So first thing we hit is the syntax. So syntax is easygoing. It's like an old math lesson. So we can assign values to variables, and the variable R or B or whatever are port variables. So we assign this directly to the ports, and that is something that will be visible outside the block. Let's assign the value 5. So we got 5 at R. We can see that it is implicitly configured to be an output, and we got 5 outside. In contrast, if I use a port variable but don't assign it, then this must be an input. So we can see here with this small knob, Y is now configured as an input. Now let's try this out. R equals Y. Enable the lever. We have 13, and then we got 13 at R. To simulate a expensive redstone wire, we have to take the signal loss into account. So 13, then 12 where the RLC is, and 11 the next block. And that leads us to the matter of arithmetics. So, like in math, you can use parentheses to group terms. You can use plus, minus, you can multiply, you can divide, and you can do the modulo operation, so for the remainder. Let's try this out. So r equals 1 because we got, well, the 13 over here, so we got 11, then times 2 divided by 2, and so we have a remainder of 1. We don't have an odd number here. Yeah, so remainder is 1. And especially for division, we need to take a look at two things. So let's say it's simply y divided by 2. So we can have full integral numbers, which are fully supported, and we have floating point numbers that we can get as result here, which are not supported. So they are rounded somehow to the next integral numbers. And the important thing is, it's not like a merchant would round. So if I were to use the 13 of y here, so that is 6.5, and 6.5 would be normally said that's 7. But in computer arithmetics, you normally round towards 0. So even 6.99999 would be rounded down to 6. So, and this is what happens here. So we can see r equals 6. And the second thing about division is division by 0. So if I type that, we don't get an error or crash. Simply the result is 0. So if you have a division by 0, you have to figure it out yourself. So don't do that anyway. Okay, so the documentation about this is here. So we got plus, minus, times, or multiplication. We got division and the remainder. And now the last thing to mention is port variables versus any kind of state variables you choose for yourself. So you can use any kind of variables, like a is y, let's say times 10. And then I say, just to depict that, r equals a. So r is 15, but I mean y 13, so 130 that we can see here assigned to a is beyond the Redstone range, and output ports are always clamped to values between 0 and 15. And that is almost everything. That is actually everything to know about the arithmetics of the RLC. Yeah, so maybe one thing, the value range of the variables is 32-bit, so that's a very large number. You will likely never hit it. Very likely. Okay, next up would be the logic. So how do logic operations work in the controller? Let's see, we have the logical operations AND, OR, exclusive OR, and NOT. So if I were to type red equals yellow and blue, enable the controller, then we can see blue and yellow are inputs, red is output, nothing surprising. The output red is off because both of the inputs have to be on. And if you remember what we discussed in the very beginning, so inputs of logical operations are designed in the way a redstone lamp would react, and the output is like a lever would output. So 15 or 0 for the output of an operation and non-zero check for the input of an operation. Let's try this quickly out. So we got yellow but not blue, so it's off. If I enable both, we have an on signal. If I remove the yellow signal, it's off, and it's also off if both are off. So simple AND operation. You can experiment that if you're not sure how the logic works. Simply use some levers and see what happens when. We'll just very briefly take a look at this because there are more things to take a look at. So OR operation. This is not the either OR, which is the exclusive OR, I will show later. This is the electronics or computer scientific OR. So that means either Y is on or B is on or both. So if at least one of them is on, then the output will be on. So we got B, we got Y, we got both, and if both are off, then the OR operation returns off, returns a low signal. In contrast, the XOR, exclusive OR, is either B or Y, so B or Y, but not both, either B or Y. And then finally we have the NOT operation, and NOT means it's a unary operation. Okay, so I can only say not Y. Y, so Y is on, that means R is off. Y is off, so R is on. Now there's one final thing to take into account, and that is operator precedence. In math, you know, b times 5 plus 3, you know that the multiplication is always calculated before the addition. And for logical operators, there's also some kind of operator precedence. So the NOT is the most important one, so it has precedence over all others. And then is the AND operation. So just say AND B. And after that is the OR and then XOR operation. Let's use green port here. So if I wanted to have B or G calculated first, then I must use parentheses. Otherwise, it will first calculate this term, like so. So you will get different results then. You have to know the operator precedence. If you are unsure, and maybe also simply to emphasize what you want to do, you can use parentheses wherever you want. So you can also make parentheses only around the G port. If it makes sense or not is now a different thing, but if you're not sure about the operator precedence, use parentheses to emphasize what you want to do. Okay. So much about logic, basic logics. Now we have another thing. We can convert arithmetic values into logic values, and that is by comparison. Let's take a look at this then in a minute, because I need a coffee. If I were to ask you if the input signal on the yellow port is greater than 12, then there are only two answers you can give me. Equals yellow greater than 12. It's either yes or no, and not 42. And these logical output signals we get are again 0 or 15 in the same manner it is for logic operators. That's pretty much all to say about it. Let's quickly try it out. So we got yellow 0 is of course less than 12, and then we get 13. It's greater than 12, and then we get our on signal on red. Now that applies to all the comparison operators. So we got equals, not equals, greater or equal, less or equal, greater than, less than. That's pretty much all you need. And they, of course, these comparisons also work for normal variables and values beyond the Redstone range, of course. One thing to mention, you can use the output, the truth signals, directly as numbers again. So you also can say divided by 3 again. So you can do arithmetics directly with the output signal of a logic operation. I forgot to mention that before. Simply to either scale your Redstone signal or do any kind of other calculations that you want to experiment with. But yeah, that is possible. So the logic values are in the end also numbers. Right, so the next thing I think would be to take a look at the function reference, and after that add timers and counters and edge detectors. Let's start with the if function. I directly say if function because if is not a program flow control keyword as known from many languages. So we don't have if condition then do something, otherwise do something else. we always need to return a value because every line is calculated and every line needs to be assigned somehow. So why is it called if? Well, because the meaning, what it does, has something to do with if branch or else branch. In this case, we have a condition x, so x, a, and b, as you can see in the first line, are only placeholders. So if the condition x holds true, then the a value is returned, otherwise the b value is returned. Now, for functions, the positions of the arguments are important. X, a, and b are only placeholders. Let's try it out. So r equals now the function name if, and then in parentheses we got the arguments. So first the condition, we say y is greater than 12, then we want the value 5, and otherwise we want the value 2. Let's start this. We get 5 because y is greater than 12. If I switch it off, we got a 0 signal on y, and we have the else value, which is 2. Now I can strip off the else value for shortening the if. So if has optional parameters, optional arguments. So if I strip the last one off, then it is implicitly presumed to be 0. So now we get a result of either 5 or 0. And if I strip off the value of 5 as well, then we have only one argument, only the condition. And then it will be implicitly thought of to be a Redstone logic signal. So then we have 15 or 0. For this expression, that doesn't make much sense because it's anyway what y greater than 12 returns. So we don't need the if function here at all. Okay, so that would be if. Now let's take a look. The inversion. Okay, Redstone inversion, not too often used, to be honest. I say I want to invert the value y. That simply means if y is 0, then the output will be 15. If it is 1, it will be 14, 2, 13, and so on. So we always get 15 minus the input value. So that's somehow the complementary Redstone value, analog Redstone value. And the only interesting thing about this function is that if you have input values that are somehow calculated from other variables and they exceed the Redstone range between 0 and 15, then the input will be implicitly clamped. So you can have a bit shorter code using the inversion function. Otherwise, well, it's pretty much the same as 15 minus y. Then more interesting is maximum and minimum and average. So I can give this a whole list. So all the parameters, the arguments of the, let's say, the max function are optional, but you, well, have to give at least one that it makes somehow sense. So let's say I want the maximum of y and b and 5. These are 3 parameters. As said, I can add many more, as much as I want. And this function will return the maximum value of all the data in the list. So that's 5 for now, because y is off, b is off. So we got 0 from these 2 inputs. So the maximum is 5. Now let's enable y, then we will have 13, and b, and then we will have 15, because now b is the maximum. And in the same way the minimum function works, so min of y, b, and 5. Now the minimum is 5, and if I switch one of them off, then it will be 0, so the minimum will be then 0. Next up would be the average function, which is called mean, like in MATLAB. So now we just use y and b. So b is 0, y is 13. That would be 6.5, and as said before, it's rounded down, so it's rounded towards 0, so we got 6. If I switch both on, then we got 15 and 13, so the average value of that is 14, and as said again, you can extend the list as much as you like. Then the limiting function, that's an interesting one, that allows you to clamp values. So you say I want to limit the value of y, especially if it is, let's say, an analog value you get in, or a comparator override, and so on. And you say, okay, I need this value to be between 5 and 10 and not exceed that range, so that you can either calculate properly with it, or that you can output the signal and other blocks beyond are not affected in somehow a way you don't want it. So now we have 10 because y is greater than 10, so it's clamped to the maximum value. I switch those off. Now we got the value 5 because y is 0, but 5 is the minimum we allow. So that's the limit function. And then we get time and clock. And yeah, I will show this in a minute after my next coffee. Good, first time. So one day has 24 hours and one day in Minecraft has 24,000 ticks. So we can use the time function for stuff we normally would use a daylight sensor or moonlight sensor for. But let's use the occasion for doing some more interesting calculations. So let's presume we wanted to know what a real world clock would show us in hours, what the current daytime in Minecraft is. So I would fetch the value first. So let's say dt, like day and time, equals time. Okay, now let's see what the value is. So it's morning. That means like 0 is sunrise. That means 12,000 is sunset. So 6,000 is noon. So we are late morning now. And now let's calculate something. So the real world clock would say in hours. Now we need to rescale that. dt divided by 1000. Then we are in hours from 24,000 to 24. And now we would have 0 o'clock is sunrise. We want 6 o'clock to be sunrise. Okay, that's at 6. And now we have, we need a wrap over because we have a range between 6 and 30. So I'll add parentheses to emphasize what the order of calculation should be. So say modulo 24, and now we should have the time in hours. So that's 11 o'clock, so that's almost 12 o'clock, almost noon. And there we go, 12 o'clock. Now we can simulate, let's say sunset. I will comment out the time, and we would say it's 12,000 ticks. And that would be 18 o'clock, so that's 6 o'clock in the evening. Perfect that. So next up would be the clock function, I think, which is kind of the official Unix timestamp in the game. So it returns the number of elapsed seconds since the game has started. So let's say clock equals clock. Now we get a very large number, which is not interesting itself, but interesting is what we can do with it. Let's presume we want to do some distributed scheduling. So you have process control over a few RLCs which are not connected to each other. And we wanted to use, let's say, to drop something with droppers. So then I were to rescale the clock value from ticks to seconds, and then let's presume I wanted to do that every second. So I would say module division by 60. Now we will have a wrap over value in seconds that wraps over from 59 to 0 again. Let's see, so 6, 7, 8, and so on. And you can already see where this is going. So I have now in the first RLC, I call it dropper 1 here. I would say this one should trigger after 10 seconds. The second one should trigger after 20 seconds, and the last one should trigger after 50 seconds. So, because every RLC sees the same clock, they will calculate the same C at the same time point, and so we will get the signals to the droppers synchronized in that way. Now there's one little thing to keep in mind though, and that has to do with performance and scheduling. So the clock function is a good thing for scheduling in a second range and synchronizing multiple RLCs with these kind of tick rates. But if you try to do something with, let's say, 1 or 2 ticks, then you need to use other timers, because the clock function is not, let's say, accurate enough for that. The clock function itself, in every tick when the RLC calculates, returns the correct value, no problem there. But the RLC, for performance reasons, does not calculate every tick. So by default, it calculates every 4 ticks, like a hopper. And if something changes on the input, so if an input signal changes from on to off or vice versa, then the block will reschedule the calculation to the next possible time point, which is normally the same tick, but I can't guarantee that because it's controlled by the game itself. So we might have 1 tick delay. I don't mean a redstone tick, I mean a game tick. This is why we should use special timers for correct tight timing. And these timers, we will go into these at a later point. They have a feature where the block knows when the time has elapsed and reschedules exactly to that time point if nothing happens in between. So timings with PLC timers will always be accurate, and if you use clock, you can use that for, let's say, a second or half a second range. It will be good enough. But if exact timing matters, then use PLC timers, not the clock function. It's important to say, because otherwise you will be debugging forever and you won't know what happened. Okay, we have, I think, 1 function left. Yeah, the random function, that's an easy one. So let's say ret equals RND. So every time the RLC recalculates, you will get another random redstone value. As simple as that. So for the very new, because it is listed down here, for the very new versions of Redstone Pen, there is the TIV1 and TIV2 interval pulse timers. So that's exactly one method to resolve these clock issues for the ticks. So let's just show it quickly. I get a pulse, let's say P, it's directly assigned to R, it doesn't matter. So TIV timed interval 1. I will talk about instances in a minute. And let's say we want to have that every 20 ticks. So now we will get a pulse every 20 ticks. The UI doesn't update every tick, so we won't see it here, but the redstone lamp is something you can see that it happens every 20 ticks. And this tick timing is accurate as well. So this will be rescheduled in a way that the 20 ticks are definitely constant. Okay, so much about functions. Now let's go into edge detection and timers and so on. Now we are somehow reaching the more interesting stuff where you can do more with the controller itself. Okay, let's drag some edges. So let's say R equals Y, that's what we typed in the very beginning. Now let's presume we are only interested in the change of the yellow port, and in particular the change from off to on. That's called a rising edge. Let's see what happens. So rising edge is if I activate the lever now. So we got a pulse on R, and then R is 0 again. Why is that the case? Well, we get the edge only the moment when we switch on. After that, the signal here is steady. It's not an edge anymore. Now, if we switch the lever off, we get a falling edge, which we don't drag in the controller at the moment. So nothing happens on R. Now we have a steady 0 signal again, and so on. Now we had a rising edge, falling edge, rising edge, falling edge, and so on. And this is everything about edge detection. It's used quite extensively, and it's really a very useful feature. But it's also a very simple feature and not really too much to tell about it. So falling edge is we write FE, and rising edge we write RE. Now the only thing to mention is, remember the clock we used, the clock functions. Let's use this again. Clock divided by 20, so we get every second. and then very quickly say divided by 2, so we get 2 seconds, we get 1 0 1 0 and so on. So an edge is detected when a signal goes from 0 to greater than 0. So also negative numbers are, well, clamped to 0 in this logic interpretation. Okay, and I could say R equals C dot, let's say, rising edge, or no, let's write OR C dot falling edge, and we have something like a second timer. We get a pulse every second, one time from the rising edge and the other time from the falling edge. Okay, so that much about edge detection. We will come back to that when we talk about counters. Now let me grab another coffee and then we will continue with the timers. Yeah, things are definitely becoming more interesting. Okay, the timers are exactly a projection of the PLC timers from the industrial world into Minecraft, and they also have the same names. So TON means on delay, TOF off delay, and TP is a pulse timer. And the only difference is that you normally need to expensively declare the timers and configure it in PLCs. And in the RLC, we have predefined timer instances for making it a bit simpler there. So we got TON 1 to 5, TOF 1 to 5, and TP 1 to 5. It's very likely more than you will ever need in one controller. The reason why we need these instances is because we need to track the time values. So every function I told you before are, let's say, stateless functions. They react directly to the input they get. Let's say a corner case is the edge detection because it needs to know the signal before to track the edge, but that's easygoing because when acquiring the new data, you can also detect when it changes. So there is a state in there, but the state can be deduced in the same tick and can be calculated in the same tick, and therefore there's no problem. That's a different thing with the timers. Now let's start with the on timer. It's simply a delay for switching on. So it's T on, I use instance 1, T on 1. Now we need an input signal. That's Y in this case, and let's say we want to switch on after 50 ticks. So now we have a 50 tick delay between switching on Y until R is on as well. If Y at any time in this 50 ticks goes off again, then the timer is immediately reset. So that's the special thing about the on timer. Anytime the Y signal, the input signal, goes low again, the timer is immediately reset and restarts when the signal goes to a logical high level again. So when it switches on. Let's try this. So I switch on, and then after 50 ticks we get an on signal on R. I switch off and it's immediately off. Now I switch on and switch off before the 50 ticks and we won't get a signal on the red port. So really the 50 ticks have to expire and the signal has to be steadily on during that time to get an on signal on our output of the timer. So that's the on delay timer. Thank you, cat, for making noises. Right, now the off timer is exactly the opposite thing. So we have a signal that is off. Now we switch on and the lamp is lit, so the output is on. If I now switch off, then the signal has to be steadily off for 50 ticks until the output of the timer switches off as well. Okay, let's try this out. So off, wait 50 ticks, and after that the output signal goes low. Now let's double check what happens in between. So I switch on and I switch off again, and then I switch on, and nothing did happen. Let me go over here. So I switch off. After 50 ticks, the signal goes off. I switch on, off. I switch on again, and so on. And then the port doesn't change. It really only switches off after the signal is steadily off for the preset time. So that's the off timer. And now the last one is the pulse timer. I also use the instance 1, TP1. And a pulse timer just checks for a rising edge of the input. Means anytime that input switches from off to on, the timer will start, and then it will continue the on signal, so it will be on for that time, and it won't check any input changes at all. So it will give you a steady pulse for 50 ticks, no matter what happens with the input in between. And after that, it will check again for a rising edge. So let's see what happens. So I switch on, we get 50 ticks pulse, it goes off again. Now the signal changes low again. That was a falling edge, not interested. So now we get again a rising edge, and now I can do whatever I want in between. It will be always a 50 tick pulse. Okay, so these are the three most dominant PLC timers, and as said again, they are used extensively, and I also use them extensively in my setups. They are really essential for process control. Right, now last thing, the counters. More of a gimmick, but they can be quite useful. But let's go over these, and then maybe let's take a look at some setups, some automation setups I did to give you some ideas. Oh no, the comparator override. We still have the comparator override. Okay, so let's take a look at that first. Okay, so quickly the counters. So I want to count up with the instance 1 if the Y signal is on. So which is low at the moment, so let's switch it on, and then we will get steadily. But that's the problem with an undefined tick rate, a count up. So this is where the edge detectors come into play. So I can only count up as well if I say I got a rising edge on Y. Okay, let's do this. Now A is 0, 1, 2, 3. Up. Now we can also count down. Let's say we can count down with the port B, and we also use a rising edge for that. So now we have A equals 0. So 1, 2, 3. We got 3, 2, 1, and so on. And we can also count to clamped values. Now it stops at 0, but there is no upper boundary. Now if we take a look where how the counters are defined, there are also instances. So there's counter 1 to 5, and like the function pattern, we have optional parameters, and depending on how much parameters we specify, we can say if we want to count up and down to a maximum value, to a minimum and maximum value. And we also can specify a signal for resetting the timer completely to the minimum value. Let's do the last one because it's the full-blown counter use. So let's say we wanted to count between 0 and 20. So these are our limits. We want to reset the timer. Now we need another port as well. No problem there. Let's use another lever. Okay, so we use this as our reset. And so we use the green port as a reset. So A is 0, so let's count 4, 5, 6, 7, 8, 9, 10. 10 it is. We can also count down again. Okay, and now it should be 0. So as long as the green port is now set, the counter will remain at 0. If we release the reset, then we can count again. Okay. And to 20. That's a bit far. Let's simply say we stop at 5. So 1, 2, 3, 4, 5, 6, and that should be only 5. Good. So these are the counters. You can already imagine what you can do with them. You can count signals from various sources, from comparator overrides, which we'll come to in a minute, and from timing signals, from whatever. You can reset them and you can define the range the counter is valid for. Okay, so these are counters, now the comparator override or comparator output, and for that we need to change the setup a little bit. This is why I deferred this until the end of the first look at the functionality. We need to change that, so let me do that. Okay, so this is our setup. We have a dropper on the red port, then on the green port a redstone lamp, and traditionally for switching something on and off on the yellow port the lever. Now the dropper is as well a redstone sink, but also an inventory, so we can query the comparator output from that. And this is what we do right now. r.co. Now the funny thing is, although the red port is an output port, we can query the comparator output from there, because the comparator output is not per se a redstone signal. It's what a comparator output, what a comparator would generate if we were to place it, let's say, on the right here of the dropper. So then we would have a redstone signal out of that comparator, but the comparator output itself is not per se a redstone signal, so we can use it on output ports. And let's directly use it for checking if the dropper is empty. So we say it's greater than 0. So you remember, if an inventory is completely empty, the comparator output is normally 0, and if it's completely filled up, then the output is 15, and otherwise it's something in between. Now if I put 1 redstone dust in there, we will get 1 short pulse, because comparator output changes to 1, we get the pulse on the red port, and then the dropper is empty again, and we get a comparator output of 0. That's fine as long as we don't put multiple items in there, because we get only 1 click. So we need to combine this with some kind of timing function, which is not a big thing to do. So we say and we use our pulse interval, so TV1, and we say we want it 4 ticks. Now this will tick and tick and tick until the dropper is empty, but we will get no further annoying ticks all the time, because this is only calculated, or this is only holds true the whole expression when the comparator override is non-zero. Okay, so let's add the input port on yellow and the redstone lamp for completeness, so that we have an indication. Let's say we copy this one over and say, okay, our green port is the yellow and the comparator override, and we can reuse the previously assigned green value in this expression, so we get the pulses for our red port here. Let's put some stuff in there, activate the lever, and now we can see that the whole thing is active until the dropper is empty. Okay, so this is now the first inspiration where we actually see something happening, except redstone lamp off and on and lever action here and there. Yeah, but this is where things get interesting. So let's take a look. I think we have covered everything, and taking a look at the recording time now, it takes actually quite a while for going through the basics until you get to the really interesting stuff. Right, so I will grab another coffee, or have breakfast maybe, I don't know, and then I can show you what I did in the Botania automation area. And yeah, I would be interested what you did with it, or what you are planning to do with the RLC, and I don't know where the problems and where the ideas are and so on. So if you like to drop me a note either on Curse or write a mail or whatever, then yeah, feel free to do that. So okay, then see you in a minute and we will take a look at the Botania area. Okay, and while concocting the whole thing together, there were a few things crossing my mind. On the one hand, not really unexpected and also not unintended, the video has become really quite long already, so we will shift going to the Botania area into the next video, and I will wrap up here with a small errata and a small appendix. So first the errata. Two things I said wrong. On the one hand, it was this is not an odd value for a modular division, which was a result of 1. Of course, it was an odd value. And the second one was about the clock function, which returns which is the Unix timestamp of the game and returns the number of seconds. Yeah, that's the normal Unix timestamp, but the clock function returns the number of ticks in the game. I'm pretty sure you figured that out already yourself because we used it already quite extensively, but it was something that had to be rectified. Okay, now the things that I forgot to mention completely. On the one hand, yeah, making assumptions, no case sensitivity. So in this tutorial, I normally used expressions in capital letters. You don't have to do that. So you could also say in lowercase letters r equals y. It's interpreted exactly as the same thing, and you can also mix that up. You can say dropper in camel case, and dropper equals y, and then you would say r equals dropper in lowercase, and that is exactly the same variable. So the program or the language is not case sensitive. Second thing, the TICKRATE. Now the TICKRATE is something that I added more for, let's say, development debugging purposes, but left it in because it was also good for gameplay debugging purposes. So if you have the impression that something goes wrong with the timing in the RLC, or you don't know if the outside circuitry is not timing like working as expected, then you can enforce the RLC to reschedule every tick so that timing is not an issue at all in the controller. And you do that using the TICKRATE variable. So TICKRATE equals 1 is what you would say in this case. So that enforces the RLC, this particular RLC running with this particular program where this particular TICKRATE is set to run every tick. Normally, as already mentioned before, it's 4 ticks like a hopper, except something changes according to logic signals on the input ports. And the other thing is, if you have the impression that you get a performance issue, then you can increase the tick rate, the tick interval actually. So it's called tick rate, but yeah, that's whatever. So to 2 seconds, and then you can take a look if something changes, if that has an impact. Now, I tested the mod already on low spec machines and didn't have any problems whatsoever, but you never know, and this is the handle how you get to know if it is a problem or not. Right, then there was a thing with the timers, exactly. Now let's quickly use red equals, we use a pulse timer 3, we use y as our input, and let's say we have 100 tick of pulse time. Okay, if I hover here, the small, let's say, RLC symbol for debugging tooltip, then I can see 2 values. On the one hand, PT, that's the preset time or process time. That's exactly what you entered here in the argument in the second one. And the ET, that's now the more interesting one, is the elapsed time. So the time that elapsed since the timer has started. And you can use or reuse this time to do some further calculations. So I could use G equals TP3 dot elapsed time, and let's presume that we say, okay, greater equal than 50 ticks. So half the time the green port is low and the other half the time it is high. So let's see it again. So low, and then when we cross the 50 tick boundary, then we have a value of 15. So that's possible. So you can use, let's say, one timer as some kind of master timer that is started by some external signal, and then you have some other ports that behave in a process, in a sequence that you want to do, depending on the elapsed time of that main timer. And this is the way how you can do it. What else do I have here? About the if condition and sub-expressions. Okay, let's merge that together. Okay, on the one hand, I saw in various codes that were shifted around in forums that people say, I use y again now, it doesn't matter. The important thing is they say .15.0. Now, I said already, these two things are optional, and if you omit them, they will yield default values. So the third argument is the else value, so that is by default 0, so we can strip it off. And the first value is, well, by default, the logic 15 value, so we can strip that off as well if we write y greater than 0, then we can omit the if entirely. So y greater than 0 returns 0 or 15 already. Now, according to sub-expressions, let me quickly put back the if. Now, we can use the results of functions directly as an argument of other functions. If that is always sensible, is on a different page, but you can do it. So I could say maximum, to use the lowercase function name here, which is also possible, maximum of g and b, and otherwise I would like to use the minimum of g and b. So now I use the result of functions as arguments of another function, like if here. It's possible. If it is always a good thing to do is another question, but you can do it. What else? PT, ET, clock in ticks, not seconds, sub-expressions. I think we covered everything here, and the other thing was, yeah, it's too long. Right, let's wrap it up here. And yeah, so if you have ideas, comments, or whatever, you can drop me that on either a comment in curse, or you can write me a mail, or you can, I think I have the mod already on Moderator. I actually need to update that there as well. Right, so I will say stay safe, have fun with it, and cheerio.